Okay, right, so just going to take you through where we get this equation from for central force. And the one we're after is F equals mv squared over r. So if we get to that point within the next 20 minutes, then that will be good. It's to do with something which is rotating in a circle, so it's going round, going like that. And so the rate at which it's rotating is the omega radians per second. And if you remember, omega is the rate at which the angle changes. D theta by dt is the rate of change of angle, and it's in radians per second because you're taking radians divided by time. And if it's going at a radius r, then the linear velocity v is related to the angular velocity how? What's the connection between the two? If something's moving at a radius v away from the center and it's doing omega radians per second, how is omega related to velocity, to the speed, linear speed? Yeah, so it's the radius times the omega. So the linear speed v is r times omega. Just in the same way that the length that you've got here, that linear length L, is equal to the radius times the angle in radians. That's what the definition of 1 radian is. Theta is equal to L over r. So for the same angle, the bigger the radius you go out there, the bigger the linear distance that you travel there. So bigger radius, bigger linear distance. So we're going to use these equations later on when we go on to this here. So to get the force, if we can find out the acceleration, then we can get the force because the mass times the acceleration is the central force that we're after. You can see that this is accelerating in because you've got an initial velocity here, VA, and then it changes its velocity, VB. Remember, the speed is the same. Those two are traveling at the same speed, but you can actually work out the acceleration if you know the change in speed VB minus VA. So if we can get the difference in those two, then we can work out the acceleration if we do that divided by the time. And so we're going to take this over a small angle of change where it changes the velocity. And if it changes the velocity from, so we've got VB here, and then the negative of VA. So if that's minus VA like that, the difference between those two is the change. That's the delta V, the change in that, and we've got that changing with respect to time. If we can get that, then we can get acceleration. That's what we're after. Now, to get delta V, we split that triangle into two. So you've got, that's our delta V, that's the change in the velocity. If we split that into two right-angled triangles, that side then becomes delta V over 2, and that angle becomes delta theta over 2. Because the thing has gone through that angle, the two velocity vectors are separate by that angle. That's where this angle delta theta is coming in. So we've split that into two halves. So the delta V divided by delta t is going to give us the acceleration. But it's how do I get that delta V in terms of the acceleration that I'm really after? Well, we've got a right angle triangle, so that means that I can say that sine of theta over 2 is equal to the opposite there, delta V over 2 divided by the actual velocity V. Now those two are the same speed, so V is the same, it's just the distance that is different, so we're just going to call them both V. And because if we take that as being a very small angle, theta, if you've got a small angle theta, what should you know about sine theta compared to theta, if it's a small angle in radians? It's a very small value, I'd agree. But what you should know is you've got small theta, sine of theta is approximately equal to theta. It's also equal to tan, but it's also equal to theta. So small angle says that if we're just dealing with a small amount of angle, then theta over 2 is the same. So we've got theta over 2 equals delta v over 2, and then divided by v. What you can do with that is then cancel the halves either side, and you end up with theta equals delta v divided by v. In other words, that the change in the angle that it describes, delta v, sorry, that should be deltas. So the change in angle is equal to the change in velocity divided by the actual velocity that you've got. That's what we've got there. So delta v over delta t. That's what we want. And that, so to get delta v, go back to what we had. So the previous screen, it was that change in angle is delta v divided by v. We're going to take both of those sides and differentiate with respect to time. If the angle is very small, we can say, well, that's all happening in a small time interval, delta t. So if we differentiate both sides, we get d theta by dt equals dv by dt times 1 over v, because that's the delta v divided by, with respect to time, we've got that there. Now, d theta by dt, from earlier on, what's the rate of change of angle equation? What was that called? How fast the angle is changing? Omega. So d theta by dt is omega. dv by dt should be familiar to you. What happens if you differentiate speed? That's acceleration. So we can now say we've got omega equals acceleration divided by linear velocity. If we replace omega, because we had that v equals r omega, so omega is v divided by r, and multiply both sides by speed, you've got acceleration is equal to v times omega. And if omega is v over r, we've got v squared over r. And so you multiply both sides by mass. So mass times acceleration equals mv squared over r. And that's the equation for the central force. Okay? So we're just using what you know about about angular motion there, relating the change in velocity with respect to time there, which is acceleration, and the change with the angle with respect to time, which is omega. Put them in together, replace v with the omega term, and you end up with your equation from that. It's not one that you need for advanced higher, but that just takes you through. The key things is that you've got this central acceleration. Things tend to accelerate in towards the center of the circle, and the reason they accelerate is because you've got that central force which causes that acceleration in that direction.